Hello class 12. In the last video we discussed about refraction taking place through a prism, and now we are getting serious about refraction, of course, here. Alright, and we are going to talk about refraction taking place through spherical surfaces. Of course we are going to talk about refraction taking place through lenses. It kind of got erased. Okay, so this is refraction taking place through spherical surfaces. Alright, so what we have is, we have a convex surface over here, and we have this convex surface separating two different media, medium number 1 and medium number 2, having refractive indices eta 1 and eta 2 respectively. Now what we consider is, we consider the refractive index of the second medium to be more than the refractive index of the first medium. So to say, the second medium is your denser medium and the first medium is your rarer medium, and thereby this spherical surface gets the name convex surface because it is convex towards the rarer medium. We also have spherical surfaces which are concave towards the rarer medium. So this is eta 1, this is eta 2, where of course eta 2 is greater than eta 1. So this is the rarer medium, this is the denser medium, but our surface under consideration here is concave towards the rarer medium. So this would be a concave spherical surface. Now what we will do in this video is, we are going to derive a relation for refraction taking place through this convex spherical surface. So we will derive a relation. We will do, of course, an elaborate derivation, which is very important for you all, and we are going to derive a certain relation. The very same relation, mind you, can be derived for a concave spherical surface also. But in a further reduced syllabus, concave spherical surface is removed. Okay, so we only need to focus on convex spherical surfaces. Okay. Now one thing I want to point out over here is, not one thing, there are many things I want to point out, okay? But see here, in this picture, let me first explain you the picture here. We have an object O, and there are rays of light actually emitted in all directions from this from this source of light O. Now, we are particularly focusing in one ray of light here. So this is the direction, and angle I is the angle of incidence, where MAC is the normal drawn to the surface at point A. Thereby C is the center of curvature, remember, the center of this part of the sphere, so to say. And since ray of light is coming from rarer to denser medium, it bends towards the normal, as you can see here, and your image I is formed at this particular point. Now I is a real image, mind you. So convex spherical surface forms a real image, and if we were to discuss about a concave spherical surface, you would get a virtual image in case of concave spherical surface. But since we are not to discuss about this, so I'm erasing it simply. Okay. Now the angle made by the incident ray with respect to this horizontal, or let me call it the principal axis. So the angle which the incident ray makes with the principal axis is alpha. The angle which the refracted ray makes with the principal axis is beta, and the angle which the normal makes with the principal axis is gamma. And P, of course, here is the pole of this spherical surface. So to say, the geometric center of this spherical surface here is what is called the pole. So in case of if we were to talk about spherical mirrors also, then in case of spherical mirrors also, so this would be a convex spherical mirror. So this would be the pole. This could be a concave mirror. Okay, sorry, not concave, this is convex, what I've drawn is. So this is your concave mirror. So this would be the pole over here, the geometric center of the spherical part. Now when we actually start discussing about lenses, we are going to talk about an optical center, the geometric center of the lens. So this would be the optical center. I've drawn a convex lens over here. You'll have the same thing for a concave lens also. So this is your optical center, generally denoted by O. Alright? So, now before we actually start the elaborate derivation, a very important thing I want to focus on, which is the sign convention. You have to know the sign convention if you are to study, optics, especially ray optics, okay, wherein we are going to talk about refraction and lenses and, okay, many other things. Alright, so you have to know the sign convention. Now, it's not that someone will ask you in the exam, write about the sign convention, okay, but you have to know this. If you don't know this, you won't be able to you won't be able to do the derivation. Also, you will be able to do the numericals. Alright, so you have to know the sign convention. I have written the sign convention for you all here, but if you understand it, it's better. Alright, now see, I want to talk about this thing first, although it's written on the sixth point. Okay, you have asterisks over here, it's important, so to say, although most of the time we take this point for granted. Remember, whenever we draw ray diagrams, we always show the ray of light coming from the left hand side, as you can see in this case also. The ray of light is coming from the left hand side of what? Left hand side of the pole. Okay, whereas if we are talking about lenses, left hand side of the optical center. Rays of light will be shown, coming from the left hand side of the optical center. Or the, left hand side of the pole, remember. Then all distances are measured from the pole of the optical center. So I'm kind of giving you a combined sign convention over here for mirrors or for spherical surfaces and also for lenses, remember, because it's one and the same thing. So if we are talking about lenses, all distances are measured from optical center. If we are talking about spherical mirrors or spherical surfaces like this, all distances are measured from the pole of the spherical surface. So in this case, from here, the distance of the object from the pole is measured to the left hand side, and object distance is generally denoted by a u. So this would be a u, object distance. It is measured from the pole. Likewise, image distance measured from the pole, this is v. Image distance is denoted by a small v. Okay, general standard notations I'm talking about. Then remember, now comes the real thing. Distances measured to the right of the pole or to the right of the optical center in case of lenses are taken to be positive. So all distances that are measured to the right hand side of the pole or to the right hand side of the optical center will be taken to be positive. This point, all distances measured to the left hand side of the pole or left hand side of the optical center will be taken to be negative. So in this case, so to say, the distance of the object, that is the object distance, of course measured from the pole, will be negative, whereas the image distance would be positive. Okay? Then distance is measured upward of the principal axis. So in case of lenses also, in case of spherical surfaces also, we will have principal axis. Distance is measured upward of the principal axis, it's taken to be positive. Distance is measured downward of the principal axis, it's taken to be negative. Alright, distance is measured upward of the principal axis, positive, downward of the principal axis, negative. Now to help you remember this, you only need to remember the x and the y axis. This is the positive x axis, negative x axis, positive y axis, negative y axis, and O is your origin. Now O, you can take it to be the pole of the spherical surface, or you can also take it to be the optical center. Now all distances to the right of the origin is positive, since it falls on the positive x-axis side. All distances on the left hand side of the origin or the pole or the optical center, it falls on the negative x-axis side, so it's negative. All distances upward of the x-axis, which is like your principal axis, it's taken to be positive since it falls on the positive y-axis side. And all distances downward of your principal axis or your x-axis, it's taken to be negative. So you can remember this to remember the sign convention simply. Okay, so my important chalk is broken. So let me therefore erase the sign convention and let us talk about the derivation. I hope you've understood the sign convention. Now let us focus on the derivation of this relation. Let me just check how long it's been. It's been 10 minutes. So I believe I can complete in under 10 minutes the derivation. So I will try to complete it fast. Okay. So let me erase the unwanted stuffs. Unwanted parts, let me erase. So this is the eta 1. Okay. So the point of incidence is point A. Coming back to this picture again. Point A is the point of incidence. Now what we've done is we've dropped a perpendicular from point A to the principal axis at point N. Okay. So how do I start? Alright. So in triangle OAC, this triangle over here, in triangle OAC, what we can write is, we can write I is equal to alpha plus gamma. Why? Because we've learned in our junior classes that the exterior angle in case of a triangle is equal to the sum of the interior opposite angles. So this is gamma. Okay, so gamma plus alpha, the two interior opposite angles should be equal to the exterior angle. So I is alpha plus gamma. This is my equation number 1. Also in triangle, which triangle? AIC. Okay. So in triangle AIC, what we have is, we have R plus beta is equal to gamma. So gamma is your exterior angle. Okay. So the sum of the interior opposite angles, or rather I can write this as R is gamma minus beta. This is my equation number 2. Okay, so therefore for refraction taking place on this spherical surface, we can write from Snell's law, what we can write is sin I by sin R is the refractive index of the second medium with respect to the first. That is what Snell's law tells us. So eta is the refractive index of the second medium with respect to the first, and this of course is equal to eta 2 by eta 1. Okay, refractive index of the second medium with respect to the first. Now this very thing can be written as therefore eta 1 sin I is equal to eta 2 sin of R. So this is what we can write. This is my equation number 3. Okay, now what we do is we consider spherical surfaces having a very small aperture. Now what is aperture of spherical surface? Spherical surfaces or that of lenses? Aperture is the distance between the two extreme points. So this distance, the distance between the two extreme points is what is called the aperture. And for all of our purpose, okay, for all of our derivations, we consider lenses and we consider spherical surface. Okay, spherical surfaces having small aperture. So if the aperture of the spherical surface is very small, then point A will be very close to point P. The aperture itself is small, so the incident ray will be somewhere over here. This is the point A. Understood? So if the aperture of the spherical surface is small, okay, then what can we write? Then A is close, or rather very close to point P, that is the pole of the mirror. This then. So in that case what happens is the angle of incidence will be very small and thereby the angle of refraction will be very small. Okay, so I and R will be very small. So if I and R are very small, what we can write is, instead of sin I, we can write I, and instead of sine r, we can write r. Okay, so if the angles are very small, then sine I is almost equal to I and sine r is almost equal to r. Remember that. So continuing, therefore, I believe you all are popping class 12. So instead of sine I, we can write, therefore relation 3 becomes eta 1i is equal to eta 2 r. This is what we can write. Or now simply substituting the value of I and r, I erase that equation. So this is eta 1. Now what was I? I was alpha plus gamma. So alpha plus gamma is equal to eta 2. What is r? It is gamma minus beta. So gamma minus beta. This is my equation number 4. Now since I don't need the lower part, let me erase the lower half here. What I need is this equation now. Furthermore, what we can write is, since the aperture of the spherical surface is very small, we've already said A will be close to P, of course, okay, and thereby angle of incidence, angle of refraction will be very small values. Furthermore, if the aperture is small, then this point N will be very close to point P, like a point A is here, the perpendicular drop, so N is somewhere over here. Okay, so therefore point P and point N will also be very small. So let me write that too. If aperture is small, then point P, points P and N will be very close to each other. And thereby what happens is the values of the angle alpha, beta, gamma will be very, very small. Point A simply is over here, so alpha, beta, gamma will be very small angles. That is, alpha, beta, gamma are very small angles. Okay, so if alpha, beta, gamma are very small angles, then what happens? What we can write is, instead of alpha, we can write tan of alpha. Why? Because tan alpha is sine alpha by cos alpha. Now if the angle alpha is very small, sine alpha is equal to alpha and cos alpha will be equal to 1. So therefore tan alpha will simply be equal to alpha, remember that. Okay? So instead of alpha, we can simply write tan alpha, remember. So that is the thing for you to remember. Let me erase this part. So therefore what we can write is, therefore tan alpha, what is tan alpha? See, look at this triangle AON. It's a right angle triangle. So tan alpha, or let me write rather this way. Therefore alpha is tan alpha, which is perpendicular by base, which is AN, divided by PO, PO, or sorry, not PO, it's no, okay, NO in this right angle triangle, the base is no. But we've already considered the aperture to be very small, so P and N are very close to each other, we've already written. So instead of no, we can write PO. So AN divided by PO. Now what is AN? AN we've considered it to be H. So H divided by, what is PO now? It is the object distance, the distance of the object from the pole, which is U. But since it is on the left hand side of the pole, so we take PO to be minus U. Incorporating sign convention, remember that. Okay, likewise, beta is tan beta. Look at this right angle triangle ANI. Tan beta is AN divided by NI, But since again P and N are very close to each other, so AN by pi, AN is h, Pi is your image distance. Now since it is on the right hand side of the pole, so it's taken to be positive. And by the way, I forgot to tell you one thing. This height h, it is measured upward of the principal axis. So therefore height h is taken to be positive, remember. So here also incorporate, actually we are incorporating sign convention. Do not forget. And finally gamma is tan gamma. In order to find tan gamma, we look at the right angle triangle ANC. So this is AN divided by NC, which is AN divided by PC. P and N very close. AN is h, positive h rather. And what is PC? PC is the distance of the center of curvature from the pole, which is called the radius of curvature. So this is capital R, the distance of the pole from the center of curvature. Now since radius of curvature is also on the right hand side, is measured on the right hand side of the pole, so it's taken to be positive. So these are the values of your alpha, beta and gamma respectively, so to say. Now what we simply do is, let me erase this part. This derivation is important for you all. And telling it again, okay? So what we do is we substitute the values of alpha, beta, gamma in equation number 4. So therefore what we get is this, we get eta 1 into, what was alpha? Alpha is h divided by minus u, h by minus u plus, what we can do is, we could have done a bit of a rearranging. So before we substitute the values, you can do it after substituting the value also, but before substituting the value, I think it would be more convenient. Equation 4 can be written as eta 1 alpha plus eta 2 beta, okay, bringing minus eta 2 beta from the right hand side to the left, of course. So this is eta 2 minus eta 1 into gamma. Now what we are doing is we are taking this eta 1 gamma from the left hand side to the right hand side, so it becomes minus eta 1 gamma, and we take out gamma common. So this is our equation number 5. Now what we do is we substitute the value of alpha, beta, gamma in equation number 5, and therefore we get eta 1 alpha is h by minus u plus eta 2 into, what is beta? Beta is h by v, h by v. This is equal to eta 2 minus eta 1. We are almost done. What is gamma? Gamma is h by r. It is h by r. Okay, so what we can do is we can take out h common on both the sides, in fact on the left hand side, and the h on the left hand side divides the h on the right hand side, and we have minus eta 1 by u, so to say, after h gets divided. So what we can write is eta 2 by v minus eta 1 by u is equal to eta 2 minus eta 1 divided by r. So this is your relation for refraction taking place through a spherical surface. Okay, to be more precise in this case, a convex spherical surface, but I told you, you get the same relation for a concave spherical surface also. If you try for a concave spherical surface, you get the same thing. Furthermore, last thing what we can do is, this only if you wish to, but sometimes you are given the relation in that form also, which we are going to do. We divide both the sides by eta 1. So when we divide by eta 1, here we get eta 2 upon eta 1. Now eta 2 upon eta 1, we've said, is the refractive index of the second medium with respect to the first, denoted by eta. Okay, so here what we can write is therefore eta by v minus 1 by u, because eta 1 divided by eta 1 is 1, is equal to eta minus 1 divided by r. So this is another form of the same relation. These two relations are one and the same. Okay, so I believe this much for this video will do. Okay, so all the best with the derivation, but understanding is very important, remember, class 12. Thank you.